Here we have this metal sphere with a radius of 80 cm, and at the center here we have a spherical cavity which radius is given by 4.5 cm, and at the center we have a positive Q. This Q is given by 5.5 microcoulombs. Now this cavity actually, that means the inside part here is just empty space. The part where the metal solid metal exists is actually the region here. Now first thing we know is that here this conductor carry no net charge. That means the total charge on this conductor will be equals to 0. But when we put this positive Q, this conductor will still have a total charge of 0. But this positive Q will attract the negative electron going into this, going toward it, and they were located at this internal surface. Now clearly they will make the outer part of this metal sphere to be positively charged, but of course the net charge on this sphere will still equals to 0, but the arrangement will be look like in the diagram I show you here, look like what I draw here. So we start with the Gauss law. Closed loop integral E dot dA. This is equals to Q enclosed over the epsilon naught, and this E, the area is the area of the sphere we define, 4 pi r squared equals to Q enclosed over the epsilon naught, and this E will equals to Q enclosed over 4 pi epsilon r squared. For case A, the R is given by 3.00 cm, which are less than the 4.5 cm. That means the Gauss surface will enclose somewhere like this, and you can see the charge this enclosed is just equals to Q. So the electric field at this 3.0 cm is given by Q over 4 pi epsilon naught r squared. This is equals to 5.50 10 to the negative 6 for pi 8.85 10 to the negative 12, and this is 3 cm squared. Here I get this is a 5.49 10 to the 7 Newton per coulombs. The direction is outward. So this is the answer for this for the A. Now we proceed to B. In this B, we know this R is equals to 6.00 cm, and this 6.0 cm. Clearly, this is less than 80 cm, but greater than 4.5 cm, right? So that means it was located somewhere here between this internal cavity and the outer surface. This is or I should say the within this metal sphere. So we know in metal the electric field is inside is equals to zero, and this is the answer for B. But in this Gauss law point of view, we can say this Q enclosed, right, is equals to Q plus this Q negative S. That means the charge you can see here is a negative charge at the internal surface, right? And which equals to Q minus Q, which finally give us this 0. And from this 0, you substitute this inside this formula. Clearly, this electric field will get 0. Well, this is reasonable because we have a charge Q. We will induce the electron which have a same magnitude around this internal surface. When we apply this Gauss surface, right, the two charge enclosed is these two charge which finally cancel out each other, give us the charge enclosed equals to 0. So the electric field also equals to 0. We proceed to C. C is given by P 0.0 cm. You can see this is greater than the 80 cm, and which if we draw this Gauss surface is somewhere here, and this charge enclosed Q enclosed in the case C will equals to Q. You can see this positive Q will cancel out with this negative Q that located at the internal surface. But now we have this positive charge at the outer surface. That means the magnitude of all this will be the same. This is reasonable because we have this positive Q at the first place. They're not really able to attract or induce more charge than the magnitude itself. So we know the finally in the case C, we enclose this whole thing will give us the Q enclosed is the same as this charge Q. So E is equals to Q over the 4 pi epsilon naught R squared. This is equals to the 5.5 10 to the negative 6 over 4 pi 5 10 to the negative 12, and this is 30 10 to the negative 2 squared. Now we just calculate for the value. Here I get this is a 5.495 10 to the 5 Newton per coulombs. Again, this is a positive charges, so the direction is the outward. This is the answer for C.